going to start with something a little bit different, which is more a sort of discussion with one of the sort of major sort of proponents of probabilistic approaches to AI about the sort of current opportunities and challenges there are in this area. So I'm going to actually invite two people up to the stage to sort of chair the discussion. We have Arnaldo Frigesi, who's a chair at Oslo. He's the chair of our external advisory board for the hub, and he's also currently sort of directing Integrate, which is a large investment by the Norwegian government into AI, into a center for knowledge-driven machine learning. So Arnaldo, do you want to come up? And then Arnaldo is going to be sort of chairing a discussion with Zoubin Ghahramani. I'm sure Zubin doesn't need much introduction. He's currently Research VP at Google DeepMind, as well as being Professor of Information Engineering at the University of Cambridge. He's done extensive research in sort of probabilistic approaches to AI and has experience both from academia, been involved in a successful startup as co-founder of Geometric Intelligence, advised a number of AI and machine learning companies, and is now working with Google DeepMind. So it's great to have him here today to talk to you.
It's a fantastic opportunity for me, Zubin, to have a conversation with you. Zoubin Ghahramani, a world leader in machine learning, right? In particular, for his foundational contributions to probabilistic modeling and based on non-parametrics in machine learning. Who are you, Zubin? And maybe you can tell us a little bit what were your main ideas in this area in the past.
Yeah, thanks Arnaldo. Thanks, Paul, for inviting me and organizing this. First of all, it's a real pleasure to be here. I feel like I'm coming back to my roots and my community. You know, it's a good question, who am I? Because sometimes I wonder who I am, because you know, the things that I do now are...
Change the answer.
Yeah. Yeah. The things that I do now are quite different from the things that I've done in the past. So just a little bit, maybe it's interesting to kind of get a sense of my trajectory. I've been very consistent. I started out interested in AI even as a teenager. I studied computer science and cognitive science as an undergrad. And then neural networks, this was in the late 80s. Neural networks were a big thing back then. And so I got very interested in neural networks, and I started working on neural networks for parsing natural language in around 87 to 90. And it didn't really work. You know, it was basically training on sentences, but we just didn't have much data. Computers were not very powerful. I never published the work. But then I kind of decided at some point after a few years that neural networks were quite boring because, you know, they get stuck in local optima and, you know, the theory is not all that interesting, or that was the sense at the time. And I really became in love with the probabilistic foundations of machine learning. So working on a number of topics like graphical models, approximate inference, including variational inference, Markov chain Monte Carlo methods, Gaussian processes, and other Bayesian non-parametric models. And then over time, I really started believing that marrying ideas from probabilistic inference with computer science ideas like programming languages was very promising, so I invested a lot of my interest into probabilistic programming languages. And then somehow throughout that whole trajectory, I ended up getting more and more involved with industry, and kind of here I am. mostly in industry these days.
Zubin, if we look to AI in general and we sort of take a bird view of machine learning today, and we look at from a certain distance, what are the important trends? And let's divide the questions in two parts. Let's look to methodological developments that are happening right now.
Yep.
And then we talk about impact.
Yeah. So, I mean, methodologically, obviously the 800-pound gorilla is large language models and large models, right? And I mean, I think everybody in the community, including myself, is just amazed at what happens at scale. And methodologically, it's quite interesting because a lot of concepts get pushed to the limits when you do things at that sort of scale. The types of architectures that you have to use, the software infrastructure. I've kind of gained a great appreciation for, you know, systems research, hardware research, and all these things that have enabled the current AI revolution that we're in, and also data, you know, understanding data, data curation, and things like that. From a kind of, you know, machine learning and statistical methodology, although some of the ideas, the basic ideas are quite simple, right? You know, like loss functions that you optimize at scale using stochastic gradient methods and so on. If you want to push the boundaries, then you have to do much more sophisticated things. So the understanding of optimization as a form of inference, I think is very interesting. Just you know, probabilistic numerics as a way of pushing the boundaries. The the real impact that diffusion models have had in terms of both image generation and other forms of video and music and audio generation, and the sort of elegant mathematical ideas behind that. The resurgence of models like state space models, I think, is also quite interesting. And so there are many, many people pushing the boundaries of methodology, even in the kind of large language model and large model space. And then as you start doing real world applications, which is kind of the second part of your question, you know, a lot of this technology is out there in people's hands, which is very different from where we were kind of a decade ago. And when you put things in people's hands, it matters when they fail, right? And so you need to think about how to make the systems more robust and reliable, and notions of uncertainty play an important role there. When to trust the system, for example, in a medical setting, let's say, or in a self-driving car. Like, you know, I would really like the self-driving car that I'm in not to be overconfident, to be able to be calibrated in its own uncertainty, and to be able to make reasonable decisions under uncertainty. Same with a medical system, but even for less, you know, maybe life critical applications like information retrieval.
You say pushing the boundaries, right? That's what is happening now. In some sense, this is a bit, as you said before, a bit boring, right? Again,
Yeah.
it's pushing the boundaries, and it's remaining in this mainstream idea, and seeing how we can scale it and how can
Yeah.
control. So, is there any new way of thinking out there that can take us probably this?
Yeah, yeah. I mean, you know, if you take the caricature of what's happening in the large model space, it seems quite boring.
Yeah.
But and there are, you know, there are people who kind of criticize it based on that caricature. If you look in more detail, though, the boundaries of building more intelligent systems involve having those systems do complex multi-step reasoning and tool use. And here is where I think things get really, really interesting. So the analogy I'll make is actually with human intelligence. Um, so, you know, we might think we're intelligent, but actually we're not all that good unless we have tools at our disposal. Me with a calculator or with a Python notebook is much more intelligent than me without the calculator or Python notebook. The same is true for AI systems. When we endow AI systems with the ability to use tools, we can get them to solve much more complicated problems. And I think this is where uncertainty and probabilistic methods can really, really shine. Because first of all, you need to know when it's a decision problem. You need to know when do you invoke the tool. Then you need to know, what do you know and what do you not know about the tool? And now let's think about what that tool could be. That tool could be a calculator, but that tool could be a simulator. It could be a logic program. It could be instantiating a graphical model and then doing, probabilistic inference in that graphical model, instantiating a probabilistic program, writing code. All of those are examples of tools. So being able to take input, understand or make decisions about what to use, then instantiate that tool, run the tool, take the output of that tool and then summarize it and give you an answer. I think that's incredibly exciting. That's certainly at the frontiers of what people are doing now.
And if we move to the application areas, Zubin, so AI is everywhere, right, and
Yeah.
important everywhere. But if you think to these new trends, what type of impacts will they open for?
Yeah, I mean, the AI is everywhere. It hasn't really impacted, a lot of our daily lives yet, right? I think the two places I would say where large models have actually had an impact are in software engineering. I think if you're a software engineer now, if I was doing coding now, I would have some sort of AI assistant helping me remember how to do that boilerplate template or debug my code. And in education, a lot of I caught my child using an AI system to help her write an essay, and she was like, "Oh yeah, we do that. I'm not really not copying, but I think it's really having an impact there. I think that as we work on more high stakes problems, again, that's where having good uncertainty quantification, good decision making under uncertainty becomes very, very relevant. And so examples of that include self-driving cars, medical applications, all sorts of places. Certainly finance, finance is all about kind of decision making under uncertainty.
Yeah. Because I think you're very right when you say that surprisingly AI is not yet so transformational as reading the newspapers, right?
Yeah.
It has not changed businesses enough. It's not changed poverty. What about climate? What about health?
Yeah.
What about food? Nothing of that, right?
Yeah.
So,
we can
so
see
what's going on there?
Yeah, I think I wouldn't say it's hype because I think if you look carefully, you see where all of these things are going. It's just it just takes time to transform things that we do. It the self-driving cars are a good example. So I spent a bit of my career at CMU. I don't know if many people are aware, but in the mid 1980s, CMU had a self-driving vehicle called Alvin that drove using a neural network. It drove on highways in Pennsylvania for, I don't know, multiple hours without human intervention. Now that's really scary in the 1980s. I would not want to be anywhere close to that vehicle. But it's taken a long time. And now if you're in San Francisco, you can actually take it, you can call a self-driving Waymo, and it can take you from one place to another quite reliably.
But I think you said something very important also before, that it's the whole environment and the whole things around AI that matter. So, I mean, there is clear evidence in science that we have to do something with the climate, right?
Yep.
And it doesn't happen. So we don't. It's not an issue of more evidence from the science. It's a political and societal.
Yeah.
So it is how that part takes in machine learning that is lacking back in some sense.
Yeah, I mean, I think that current tools from machine learning and AI can be quite helpful, but it requires a lot more effort. I'll just cite a few examples of places where things could be helpful. There's great work on using AI methods to discover new materials. So new materials, discovering new materials at scale can help us with developing new batteries or new solar panels. There is fantastic work on both weather modeling, which is interesting from the point of view of like, large-scale simulations and being able to accelerate large-scale simulations and get quantified uncertainty using AI models, as well as climate models. There is work in AI, for example, to solve complex control problems around, plasma fusion reactors, which could help, accelerate the path to fusion energy. Again, all of these can point to places where we may be able to address some of our climate problems.
Let's take a question from the audience, if there is one right now, before we move to more probabilistic AI. Is there any question from you? Yes, please.
Thank you. Thank you for the talk. It's been really nice, the chat. I have missed one particular topic, and that's the ethics underlying all of this AI revolution.
Yeah, so the question is about the ethics of AI. It's clearly incredibly important to deploy these powerful technologies in an ethical and responsible way. That's, from the Google perspective, that's one of the reasons we've been taking a sort of measured approach to how we put the AI technologies in people's hands. On balance, it's pretty clear that there are huge advantages to AI. All these examples that I cited right now in terms of, for example, accelerating the sciences or increasing productivity, even things like better entertainment, all sorts of things that we care about as human beings. But as we get more and more powerful tools, I think we need to think about, what do we as humans want from that society that we're building? So in terms of some of the challenges of AI right now, there are a lot of challenges around bias and sort of like even amplifying societal biases at scale. I think that's quite dangerous. There are incredible challenges around misinformation and disinformation, fake news, phishing attacks and scamming. I think AI methods can be used to exploit people. There are challenges around the use of AI methods by oppressive governments or in military applications. There are challenges around inequality and the future of work. And so the list goes on. I think that these are not, like, there isn't a silver bullet to solve any of these things. I think these are just massive, societal questions that need to be dealt with um, by the technologists as well as by, the public and the, uh, you know, um, non-governmental organizations and governments. I don't think technologists, I don't subscribe to the view that technologists just build technology and they shouldn't worry about it. I think that's really not uh, a healthy way of going about technology that is so impactful on society.
Yeah, and it is also possible that thinking probabilistically gives a new space in the ethical perspective of AI, right?
Yeah, I think it's, I want, um, I want my intelligent tools to understand their limitations.
Mhm.
And I think
So the car in San Francisco to stop and tell you, can you please drive now the next 200 meters? I have no idea what to do.
yeah, I mean, there are many examples. Like, one of the reasons self-driving technology has taken so long to make it out onto streets is that um, it, there is a very long, heavy tail of possible events that you need to deal with, and human reasoning can be quite good at a lot of those things, and we're not very good at our senses and our reaction times, and all sorts of other things that computers are good at. But we tend to be good at sort of dealing with weird,
Sorting out
yeah,
rapidly things, right? Yeah.
weird events, or inferring causality. I think that's another frontier
Yeah.
in the field, which is obviously very closely related to probabilistic reasoning. A lot of our large models are kind of faking reasoning abilities. If you probe them uh, around challenging questions, you realize that they don't really, quote, understand, and we need them to be much better.
And it is true that probabilistic thinking moved us from GAN to diffusion models, and we have all these fantastic models that generate text, images, videos, and
Yeah.
so on, right? And but what you say is the value of taking probabilistic approaches to AI? What is this intrinsic value of it?
Yeah, it's a great question. I've kind of asked myself this for many, many years. Um, and I tried to articulate this I had probably the paper I'm kind of proudest is I have a review paper from 2015 on probabilistic machine learning and AI. And it's interesting because it was pretty well cited, but it was in a special issue on machine learning, and the paper on deep learning has 75,000 citations. And it's a well-controlled experiment because those two papers came out in the same issue. So we, as probabilistic AI people, we still have a lot of work to do to convince the larger community of the value and importance of probabilistic AI. I've tried to do that a lot in a lot of my lectures and my teaching and my papers and so on. And I've met a lot of skepticism, right? And because I was for a while before Brain and DeepMind merged to form Google DeepMind, I was leading Google Brain, and Google Brain, it was very interesting for me to be leading Google Brain because Google Brain was a hotbed of just deep learning people, right? And I came to appreciate and really value that work. So we need to be not dismissive of the amazing progress that has been made in other areas of AI, and to see the synergies. So what value can probabilistic methods bring? First of all, I think that making advances in the field still requires deeper understanding of the mathematical foundations of machine learning, and probability theory is basically, absolutely central to the mathematical foundations of machine learning. I think probability theory, optimization, kind of obviously statistics as well. I also think that in practice, when you want to build real systems and you want to deploy them, you realize that the bar is pretty high in terms of the abilities of the systems that are needed. And then probabilistic methods can come to the rescue. I'll give you a nice example of that. So we had a project which is still ongoing at Google, which is a system called Derm Assist, which basically takes a mobile phone and you can take a picture of your skin, and it can try to come up with potential things that it could be. So think of it as a diagnostic dermatologist in your pocket. You can imagine that's quite valuable because there are literally billions of people now that have mobile phones with cameras. Getting an appointment with a dermatologist is out of reach for many, many people. And a lot of people worry about skin conditions. Of course, the challenge of building a system that really works is it needs to be reliable. It needs to work on different skin tones. So it needs to be sort of equitable across societies in the world. But also it needs to be able to say that it doesn't know. And it needs to be able to quantify uncertainty. So it's an open class classification problem where the number of skin conditions is not like K classes and that's it, right? There may be like K high frequency classes and there may be a very long tail of other things. And so, we had some of our, probabilistic modeling and uncertainty quantification folks work very actively with that team to deploy that product. And that product just would not have been successful if it, confidently gives the wrong answer or if it's not aware that it could be something it's never seen before.
No, they have to give the right answer when it's easy. Yeah. And with a sharp credibility interval in some sense. Yeah. And then it should be broad when it's unclear.
Yeah.
Yeah. But this means that we have to be able to really quantify this uncertainty properly. Yeah. Are we able to quantify uncertainty? Are we near to really being able to do that job?
Yeah,
because maybe they're right. That they don't want to have our credibility intervals because they're rubbish.
Yeah, I think quantifying uncertainty is a very, very hard topic. For a few years, I fell in love with Gaussian processes because they're very elegant and simple in terms of being able to quantify uncertainty. But even there, you're from a subjective, and I spent most of my career kind of thinking of things from a subjective Bayesian point of view. Even from a subjective Bayesian point of view, you're quantifying uncertainty conditioned on some assumptions, and then you need to really question those assumptions, like, have I captured the uncertainty in the kernel, for example? Have I captured the uncertainty in the in the possible noise models that I could have, and so on. So even for a simple model like a Gaussian process, I don't think we can really quantify our uncertainty very well. Of course, from a subjective Bayesian point of view, you can come up with a prior and really, just crank through that using your best approximate inference methods that you have. But then when you get to the current state of the art in AI, which is large models, most of the models out there have literally billions of parameters, some hundreds of billions of parameters. Good luck, trying to quantify uncertainty over parameters there. You can't even hold one instance of like all the parameters in memory often. And so, you certainly can't, capturing error bars or samples of the parameters is very, very hard. And so you need to be more creative. And we have a lot of folks who've tried to think of creative ways of getting a little bit closer to understanding the uncertainty.
Maybe we need definitions of uncertainty that are clearer, what type of uncertainty they really capture and what they don't. That's fair enough, right?
Yeah. Yeah, I mean,
I mean, the uncertainty that comes from approximated algorithms, for example, that comes on top. I mean, in all statistics, we have
yes,
difficulties in quantifying uncertainty already, as you
yes.
say, with model choice. Then it comes in these big models, all the algorithms on top of it, right?
Yeah, yeah. I mean, I've struggled with that question, you know, because you know, even if you're a subjective Bayesian and you say, well, I'm going to try to, you know, come up with a prior that really captures, you know, my beliefs, and then I'm going to apply the best methodologies that I have. The uncertainty that comes, you can't do exact inference in most models, and the uncertainty that you get from your approximate inference methods, your algorithms that you use. Um, that's a really interesting question to figure out, right? And that's where I think actually the marriage of um, Bayesian and frequentist methods is actually quite interesting. You know, you could say, well, I'm going to crank through my, you know, fully Bayesian approaches, but I know that I've made a whole bunch of approximations along the way. Maybe I need to look at a sort of frequentist lens at the end um, to gain some confidence in what I have and to be able to communicate it to others who may have different priors, for example.
And then, I mean, one of the big thing in this neural network are the embeddings, these
Yep.
high or low dimensional summaries that can be transported to other things. That's really
Yep.
a miracle. But they are also very uncertain, of course, right? And this is completely ignored today.
Yeah.
And this seems to me a terrible danger, right? And maybe that's the reason why things don't work.
Yeah. Yeah.
So what can we do there?
Yeah, it's interesting. Uh, you know, and it, first of all, it's certainly true that probably the most interesting thing about neural networks is the fact that they take data and they create high dimensional distributed embeddings. It's sort of like PCA or factor analysis 120 years later, um, on steroids, right? With billions of parameters and nonlinear and so on and so forth. Um, Now, those embeddings are very, very powerful. They create, like, with enough data, they create rich representations of your data that can be reused. Um, we we don't think. I mean, I've tried to think about, like, what does it mean to have um, distributions over embeddings? Is it practical? Is an embedding is it an inference problem or is it a decision making problem? And I think actually it might be a decision problem in the sense that, and in that case, it may not make sense to have um, a distribution over them. If there was something like a true embedding and you're trying to infer it, then it makes sense to capture the uncertainty over the embedding. But if you think of embeddings from a decision point of view, you're taking data and you're trying to use a nonlinear function to map that data to a vector that ends up being useful across many different tasks, downstream tasks, then there may be kind of a decision theoretic way of saying, well, this is the best vector that will perform best on these different tasks, or that is expected to perform best on this distribution over tasks, or something like that. There'll still be uncertainties in there, but if it's a decision problem, then maybe point estimates are fine. So I'm not 100% sure of that. I think, I mean, I kind of wondered about this in a workshop maybe 10 years ago, and then I thought maybe there's a paper worth writing about it, but I didn't, I don't think I got far with that.
We can try again. Questions from the audience? More questions from the audience? Yes. We start.
I think
You want to try that
lady in the
microphone?
back.
It works?
Lady in the back had her hand up before. Yeah.
Let's see if it works.
Thank you very much for all the conversations. I wanted to ask about these big models. So I understand that from industrial point of view, it's very beneficial to have one big model. Yes, it's expensive to train, but then you can reuse it. You can tune it, reuse it to apply to different problems. But are these models really much better than a model that is, for example, constrained on physics or chemistry? Are they better at performing certain tasks? What's your opinion about this?
Yeah, that's a great question. Even within an organization like Google DeepMind, we actually had a meeting a few months ago where we organized debates, and one of the debate questions where there was disagreement was, do we need one big model or do we need many specialized models? I don't remember what the outcome of the debate was, but I remember that basically people were quite divided on this. I think the first of all, it depends a lot on the application. Secondly, I think that we can have our cake and eat it too in the following way. So we can take single large models and use them as general representations of a lot of different kinds of knowledge, and then build on top of them specialist models that may be targeted at a particular application. So for example, if you're trying to solve a particular chemistry problem, you could just build models around chemistry problems, or you could build a very general model that actually knows about chemistry, biology, physics, and then it might help you. It might transfer information to then fine tune that model or add a few layers to that model that will then specialize for that particular task. So that's the kind of approach that people have used for these sorts of problems.
Thank you. You said you would like your model to say that it doesn't know. And I think that's an interesting aspect. And I wonder if we have the right tools for that. If we express our knowledge about something, we might be uncertain and we know that we don't exactly know, but sometimes we know exactly that we don't know. Do we have the instrument to express in a model that it confidently does not know?
Yeah, it's really difficult. This is like, was it Rumsfeld? There's a great quote from Donald Rumsfeld on the things that we know we don't know, and things that we don't know, right? I think that we have a lot to go. Like we can't even do basic forms of uncertainty in a lot of these models. They should really be able to. A good example of this is if you give a lot of these models, garbage inputs, like kind of nonsense inputs, it, it, it might confidently produce some output. And it doesn't even express the uncertainty that it has. It should just say your input is garbage. I don't understand what you're saying, right? But then there might be other places where the model thinks it knows. I'm using, a lot of anthropomorphic language, but I think everybody does these days. The model thinks it knows, but actually it doesn't really know. Yeah, but probably, we'll keep having to struggle with that. By the way, humans are not very good at this either, so.
So I had a question about academic compared to industrial AI research. So probably of the last sort of 10 years or so, we've sort of seen more people with PhDs sort of leave academia and go into industry. We've seen all the sort of compute that's available in industry. So I guess my question would be, what should academics be focusing on? What are the sort of impacts that academics can make around probabilistic AI?
Yeah, that's a great question. I've sort of had a mixed career myself. A lot of my colleagues also have mixed careers. They have like some part university appointments or part industry appointments. I'm a big believer in that. Actually, I think it's quite useful, even if even if it just involves doing an internship or two in industry. I think it's a really, really valuable experience for PhD students, just to understand kind of how industry works. I always encourage all my PhD students to do a couple of industry internships. And the program here I think is great because it's also encouraging that fluidity. Now, so the question is really like what should the academic world focus on? There are a few things that are very different. So one of them is the incentive structures. So although from the academic side, it might seem like, oh, these industry researchers can work on whatever they want. There are actually very few labs where that's really true, right? And even within those labs, the way the incentives are structured are in terms of questions around like, well, what impact are you having on other teams? What impacts are you having on the products and so on? And certainly a lot of people are now moving into startups. And if you sort of join a startup thinking that you're going to be able to do basic research, I think, good luck. You'll be doing something very different within 2 weeks. Um, in academia, I think we have the luxury and the privilege to be able to think deeply about problems for long periods of time and to really forge unique areas of expertise. So a lot of the work on the foundations of machine learning and AI will continue to happen in academia. We have, I think academia also has the great advantage of being a place where you can, train people and influence the next generation. I think that's a big advantage that academia has. Even within the large model space, there are many, many models now that have been made openly available. So, even, Google just released like Gemma open models recently. These models are not that big that, you can actually use them on an academic. You can actually, use some of these models on your laptop, or you can use them in certainly on a cluster, an academic cluster. I think the harder thing is if you want to do research on scaling, the large scale models work, training large scale models, that's probably best done in industry still. But there is a lot that can be done using the models as tools. So building on top of those models, whether it's through fine tuning them, understanding properties of these models, and so on. Then the other advantage that industry has on the other side is when you work on real products, you understand the limitations of your methods very quickly. A great example of this is research on factuality in large language models. So, language researchers have worked on factuality for decades, but if you actually try to build a tool that millions of people use, then you discover, hundreds of thousands very quickly of examples of failures, and that can inform where to do your next research.
I think that we have to conclude our very interesting conversation. Thank you very much, Zubin, for this fantastic conversation.
Thank you, Arnoldo.
And we will really follow ProbAI, the hub, in the next years, and I think you will enjoy following their groundbreaking results in probabilistic AI.
Yeah.
Thank you very much, Zubin.
Yep. Thank you.